Follow the line of moving green, and you might think the forest floor itself is in motion. The leaves seem to walk, each fragment wobbling in rhythm as though carried by invisible hands. But beneath every trembling shard is a worker, one of millions, carving out her role in one of nature's most astonishing civilizations. The leafcutter ant's empire is not built of stone or wood, but of soil, saliva, and fungal threads, woven together in an ecosystem that hums quietly below our feet. To an untrained eye, the ant's procession is simple. Climb a tree, cut a leaf, haul it home. Yet this endless relay is not a matter of feeding the colony directly. The ants do not eat the leaves they labor to harvest. They are farmers, and the leaves are only raw material, gathered to feed another life form entirely. Deep beneath the soil, where air grows still and light disappears, lies the true heart of their civilization, vast fungal gardens that sustain the colony's every member. The journey from canopy to chamber is treacherous. A single worker may travel hundreds of her own body lengths while balancing a leaf segment far larger than herself. To conserve energy, traffic on the trail flows with remarkable order. Outbound foragers hug one edge of the path, inbound carriers keep to the other. They follow chemical cues, pheromone trails laid down like living road paint, guiding them with precision that rivals any human-made highway system. When an obstacle blocks the route, engineers gather instantly, linking their bodies into living bridges and chains, allowing others to pass over. This is not chaos, but choreography, a pulse of cooperation that keeps the superorganism alive. Above ground, danger lurks at every turn. Parasitic phorid flies hover like vultures, waiting for a chance to lay eggs inside an exposed worker. To counter them, the colony employs bodyguards known as minims, the smallest caste, barely larger than a grain of rice. These minims ride atop the leaf fragments like cavalry on steeds, scanning the air for danger. If a fly dives, the minim lunges upward, batting it away with furious precision. To the casual observer, this tiny passenger seems ornamental, but to the colony, it is a guardian of productivity. Every harvested leaf carries not only a future meal for the fungus, but the survival of an entire workforce. Back at the nest entrance, the flow of green disappears into darkness. The descent leads to an engineering marvel, chambers and tunnels that can stretch several meters deep and span the area of a small house. The air inside is heavy with humidity, carefully maintained by workers who constantly adjust soil ventilation and moisture. Too dry and the fungus wilts, too wet and it rots. The entire structure functions like a living lung, inhaling fresh air through upper vents, exhaling stale gases through lower chambers. Temperature and airflow are balanced with instinctive precision, as though the colony understands the physics of respiration. In the fungus gardens, a different caste takes over. These are the gardeners and nurses, pale-bodied and soft from spending their lives underground. They chew the leaf fragments into pulp, mixing them with droplets of saliva that inoculate the material with fungal spores. But not just any fungus will do. Each colony cultivates a specific species, Leucoagaricus gongulophorus, a symbiotic partner passed down through generations. The ants feed the fungus, and in return, it produces nutrient-rich nodules called gongilidia, the true food of the colony. Queens carry a pellet of this fungus in their mandibles when founding a new nest, ensuring the legacy of the farm continues. As the leaf substrate decomposes, it becomes a breeding ground not only for the cultivated fungus, but for unwanted guests. Parasitic molds, especially of the genus Escovopsis, threaten to invade and destroy the crops. Yet evolution has armed the ants with a remarkable countermeasure. Many workers wear what looks like a dusting of white powder on their shoulders, not debris, but a living armor of bacteria. These actinobacteria colonies secrete natural antibiotics, which the ants spread across the garden as they work. It is one of the oldest examples of biological pest control, a microbe domesticated by an insect to defend another symbiont. Long before humans discovered penicillin, these ants were running their own pharmaceutical operation underground. Waste is no less managed. The colony maintains strict sanitation zones, distant chambers where refuse and old fungal substrate are dumped. Special waste workers, often sterile individuals nearing the end of their lifespan, handle this toxic duty. They rarely return to the main tunnels, minimizing the risk of contamination. Their sacrifice ensures the safety of millions. This division of labor, down to the level of disease management, shows an intelligence not of individuals, but of the system itself, the emergent mind of the superorganism. The queen lies at the core of this organism, deep in a protected chamber surrounded by attendants. Her body is immense compared to her daughters, swollen with eggs that number in the tens of millions over her lifetime. She is the genetic engine of the colony, yet utterly dependent on her workers. Without their care, her reign would end in hours. Without her, their society would collapse within weeks. Together, they form a single biological entity, one heart, countless limbs. Every action within this subterranean city is tuned to ecological efficiency. Leafcutters act as the forest's silent recyclers, breaking down plant matter too tough for most herbivores. In doing so, they accelerate nutrient cycling, returning carbon and nitrogen to the soil. Their fungus gardens enrich the ground with organic material, influencing plant growth across the ecosystem. Even their waste heaps become fertile islands for new seedlings, demonstrating how one species' industry can reshape its entire habitat. Above ground, the trail continues day and night, a living thread connecting the forest canopy to the underworld below. Through the lens of evolution, the leafcutter's partnership with its fungus is a story of mutual dependence so refined that neither could survive without the other. The ants cannot digest raw vegetation. The fungus cannot exist without the ant's care and protection. Over millions of years, their relationship has become so interwoven that it functions as a single metabolic cycle. Photosynthesis captured by leaves, processed by fungi, converted into energy that fuels an empire of insects. If one could listen closely to the colony, perhaps it would sound like breathing, a million tiny lungs exhaling in unison, sustaining a life form that spans air, soil, and root. Here, beneath the forest floor, civilization is not measured by language or tools, but by cooperation and balance. The leafcutter ant reminds us that intelligence need not wear a face or wield fire. Sometimes it takes the form of endless green fragments moving through the dusk, carrying the weight of an entire ecosystem on their backs. The camera glides slowly along a sunlit fence, its wooden grain traced by the afternoon light. Then a perfect circle comes into focus, a hole so symmetrical that it seems cut by a precision tool. But there is no human craftsmanship here. The entrance belongs to a carpenter bee, one of nature's most efficient engineers, whose tools are not metal and machinery, but mandibles and instinct. The edges of the hole are smooth, polished by countless bites, each measured stroke widening the passage just enough to admit her robust body. Inside that small doorway lies a world invisible to most eyes, a gallery of tunnels and chambers carved directly into the heart of dead wood. To the carpenter bee, this timber is neither home nor meal, but a nursery, laboratory, and architectural statement all at once. She begins by chewing a straight shaft into the grain, guided not by sight but by the vibration and resistance beneath her jaws. She reads the density of the wood the way a blind sculptor might feel for shape, adjusting pressure to maintain an even bore. Once deep enough, she takes a sharp turn, extending her tunnel along the length of the grain. This lateral passage becomes the main hallway of her brood gallery, a hidden structure lined with compartments that will each hold the next generation. Every cell she builds is a story of careful resource allocation. At the far end of the tunnel, she deposits a pellet of pollen mixed with nectar, a doughy mass called bee bread. On this golden cushion, she lays a single egg. Then she partitions the chamber with a wall of compacted wood shavings, a plug she creates by chewing her own sawdust and pressing it into place with rhythmic strokes of her head. When the seal is complete, she begins another cell just behind it, repeating the process in reverse order, stacking her offspring like beads on a hidden wooden thread. The result is a row of perfectly spaced nursery chambers, each a self-contained microcosm of development and sustenance. From the outside, the wood remains unremarkable, silent, unchanged, yet within life hums. The larvae that hatch in those sealed cells consume their pollen bread slowly, transforming its stored energy into the delicate architecture of wings and muscle. Weeks pass, unseen. The tunnels remain quiet, except for the faint rasp of mandibles or the low, resonant hum of a bee shivering her thoracic muscles to generate heat. When the time comes, the adults chew their way forward, each one emerging into the light through the same immaculate round doorway, the signature of the carpenter's lineage. The females, broad and metallic, are the true builders. Their black and gold bodies gleam with a matte sheen that catches sunlight in iridescent flashes. The males, slightly slimmer and often fuzzier, lack the sting their partners carry but compensate with attitude. During mating season, they hover like miniature drones, patrolling the airspace near nest sites. They buzz aggressively at intruders, including humans, projecting authority through volume alone. Yet their bluster is harmless. Their loud flights and confrontational dances are a bluff, a defense strategy built on deception rather than danger. The females, meanwhile, go about their carpentry in stoic silence, ignoring the chaos above. Contrary to popular fear, carpenter bees are not destroyers of homes. Their work is deliberate and selective. They prefer untreated, unpainted and sun-warmed wood, the weathered ends of a log, a dead tree limb, or an old fence rail. Painted or pressure-treated wood rarely attracts them. It is too dense, too foreign. Unlike termites, they do not eat the timber they bore into. The chewed fragments serve only as building material for partitions and plugs. Over generations, a family of bees may reuse the same gallery, extending or branching it slightly with each season, but never spreading like an infestation. Their presence is surgical, not parasitic, more like a cabinet maker's careful touch than a vandal's destruction. Step into a summer meadow, and the carpenter bee's other masterpiece reveals itself, not in wood, but in air. Here, among the flowers of tomatoes, blueberries and nightshades, she performs a feat few other pollinators can replicate: buzz pollination or sonication. Many plants keep their pollen locked inside narrow tubular anthers that refuse to open under mere contact. The carpenter bee approaches these blooms with purpose, grasping the flower's base with her mandibles and curling her legs around it in a tight embrace. Then she flexes her thoracic muscles, the same ones used for flight, but keeps her wings folded still. The result is a deep, vibrating hum that resonates through the flower at a precise frequency. This vibration shakes the pollen loose like dust from a sieve, releasing golden clouds that coat her body. The spectacle is both scientific and symphonic. Each species of bee has its own unique frequency, tuned by evolution to match the resonance of specific flowers. For the tomato blossom, for instance, the vibration must reach hundreds of cycles per second, a rhythm perfectly matched by the carpenter bee's muscular machinery. What emerges is not random noise, but a biological waveform honed over millions of years. Buzz pollination provides a crucial ecological service. Many of the world's crops, from potatoes to cranberries, depend on this vibrational method to reproduce. Honeybees, for all their fame, lack the ability. Their flight muscles are built for endurance rather than resonance. Carpenter bees, however, are the virtuosos of vibration, natural instruments in the grand orchestra of pollination. Without them, entire plant lineages would struggle to seed and fruit, reminding us that even solitary bees play a role disproportionate to their numbers. Their evolutionary success also lies in thermoregulation. Carpenter bees can fly in cooler conditions that ground other insects. By decoupling their flight muscles from their wings, they can shiver to raise body temperature before takeoff, a form of internal preheating. This ability allows them to forage early in the morning or on overcast days, when flowers are still heavy with dew, monopolizing resources before competitors arrive. Such physiological control highlights the bee's mastery of energy. It can generate warmth, modulate vibration, and calibrate flight, all through precise mechanical use of muscle fibers smaller than a grain of sand. Inside the galleries, parental investment continues long after the drilling ends. Unlike many solitary insects that abandon their eggs immediately, carpenter bee mothers often guard their tunnels, warding off predators such as parasitic wasps or ants. She will hover at the entrance or retreat deeper within at the first sign of threat, her mandibles ready. If disturbed, she may even block the doorway with her head, a living door keeping danger at bay. Her care extends to cleaning, repairing, and occasionally provisioning the brood chambers until her offspring are nearly ready to emerge. This maternal vigilance increases the survival rate of her young, a behavior that blurs the line between solitary and social living. The carpenter bee's influence extends beyond her own species. Abandoned tunnels become valuable real estate for other insects. Solitary wasps, small beetles, and even spiders seeking refuge. The galleries, in effect, become part of the ecosystem's architecture, recycled through generations of occupants. Each hole drilled into dead wood increases surface area for fungi and bacteria, accelerating the decomposition process and enriching the soil below. Thus, the bee's engineering, often misread as destruction, is in fact a quiet form of ecological restoration. As the camera pulls back, the once suspicious hole in the fence becomes something else entirely. A portal into a hidden continuum of labor, evolution, and adaptation. Within that small space lies evidence of biological precision unmatched by human tools. The carpenter bee drills not for destruction, but for continuity. Her tunnels are blueprints written in wood grain, evidence of craftsmanship evolved through patience and necessity. When she lands once more on the weathered board, sunlight glancing off her dark exoskeleton, the sound that follows is neither a buzz nor a hum, but the vibration of purpose. The perfect drill resumes its rhythm, and the forest listens, as it has for countless millennia, to the work of an architect who builds not monuments, but legacies. Suspended between branches in a shaft of sunlight, a glint of gold trembles against the forest air. At first glance, it could be no more than a stray thread catching the morning light, but as the camera drifts closer, that shimmer resolves into geometry. An orb of near-perfect symmetry, anchored at multiple points, its threads radiating outward like spokes of a wheel forged from liquid amber. This is the domain of the golden silk orb-weaver, an architect whose craft merges biology and physics so seamlessly that every strand performs a function honed by millions of years of trial and error. Her web is not a random tangle, but a blueprint of mathematical precision. The foundation begins with the drag lines, non-sticky structural threads extruded from specialized spinnerets. These form the frame and spokes, the web's skeleton. The spider releases them while suspended, guided by nothing but gravity and air currents, adjusting tension by minute changes in leg pressure. Once the skeleton is stable, she switches to a different kind of silk, the capture spiral, coated in microscopic droplets of glue-like material that give the web its golden sheen. To the human eye, the result looks decorative, like molten metal drawn into air. But its function is pure physics. That golden hue is more than aesthetic, it is a lure. The silk reflects ultraviolet wavelengths, similar to those emitted by certain flowers and foliage, tricking day-flying insects such as bees, butterflies, and even small wasps into approaching. The effect is most powerful at low sun angles, dawn and dusk, when the web's reflective properties blend with the color temperature of ambient light. Some studies suggest that the hue also camouflages the spider against the background glare of sunlight, allowing her to remain invisible while the trap itself gleams invitingly. Thus, what appears to the human eye as beauty is, to the spider, a biological illusion, the shimmer of hunger disguised as gold. Each thread of silk is a masterpiece of molecular engineering. The dragline silk, the core structural material, is stronger than steel by weight, combining rigidity and elasticity in a ratio no synthetic polymer has yet achieved. It owes this to its hierarchical protein structure. Crystalline regions provide strength, while amorphous segments stretch and absorb energy. When an insect collides with the web, these threads deform rather than break, dissipating the impact across the radial spokes. Meanwhile, the capture silk, those sticky spiral threads, are a different formulation entirely. They are composed of glycoprotein droplets suspended along a core fiber, each droplet able to stretch many times its diameter before rupturing. This viscoelastic property allows the web to absorb kinetic energy and restrain prey that might otherwise tear free. Humidity fine-tunes this balance. On damp mornings, the silk absorbs moisture from the air, increasing its elasticity. The glue droplets become more adhesive, their viscosity lowering just enough to trap light-bodied insects that might otherwise slip through. By afternoon, when the air dries, the silk contracts and stiffens, reducing sag and maintaining tension even as wind currents shift. In this way, the web breathes with the forest, softening and hardening in rhythm with the weather. This is hydrodynamics at the scale of silk, a responsive material that adapts moment to moment, balancing structural integrity and trapping efficiency through nothing more than protein chemistry. Placement is equally critical. The golden orb-weaver does not build just anywhere. She positions her web across open corridors of air, the invisible highways where insects travel between canopies, flowers, or streams. These wind corridors act like natural runways of prey traffic. By orienting her web perpendicular to the dominant breeze, she maximizes throughput, the number of insects that blunder into her trap per hour. Every night or early morning, she assesses damage and rebuilds as needed, recycling old silk by consuming it. The proteins are digested and repurposed into fresh threads, a closed-loop manufacturing system without waste. Even the orientation of the spiral, clockwise or counterclockwise, depends on wind direction, prey type, and available anchor points. When the web is complete, the spider settles at its hub, her long legs extended in a perfect radial stance. Each limb rests on a different spoke, transmitting vibrations like the strings of a musical instrument. Through these threads, she reads her world. A slight pluck at the edge tells her not just that something has landed, but what it is. The amplitude, frequency, and duration of the vibration encode the prey's mass, struggle intensity, and even species. She can distinguish between a falling leaf, a small moth, or a large bee without ever seeing it. Her sensitivity is extraordinary. She perceives displacements measured in nanometers. When a vibration signals a true catch, the choreography begins. She orients instantly toward the disturbance, accelerating down the radial lines in bursts that seem effortless. Upon arrival, the attack unfolds in a precise sequence: detect, rush, wrap, jab, suspend. The first contact is tactile. Her forelegs sweep over the prey to confirm entanglement. Next, she spins, using her hind legs to spool silk from her spinnerets, encasing the victim in a tight cocoon. Her movements are both mechanical and hypnotic, driven by neural reflexes that have evolved into near-perfect efficiency. If the prey is dangerous, perhaps a wasp or a bee, she administers a safety jab before wrapping fully. Her fangs pierce the exoskeleton, injecting a neurotoxin that paralyzes muscle but leaves the heart beating. This keeps the tissue fresh for later feeding. Once immobilized, the spider suspends the bundle from an auxiliary thread, hanging it beneath the web like a ration in storage. It will be consumed later when the web's traffic quiets. In the golden orb-weaver's world, energy management is everything. The act of spinning silk is metabolically expensive, requiring protein synthesis and water regulation on a massive scale relative to the spider's body size. She must balance this cost against her catch rate. Too few prey, and she may dismantle her web early to reclaim the silk's nutrients. Too many, and she risks damage to the structure from excessive struggle. The web, in essence, is both a hunting tool and a barometer of ecological balance. Predators rarely trouble her, though birds sometimes tear through webs or steal trapped insects. To counter this, some orb weavers add stabilimenta, zigzag bands of denser silk, across the web's center. These reflect ultraviolet light more strongly, warning larger animals away. Others argue that these patterns serve a different function, luring additional prey by mimicking floral shapes. Whatever their purpose, they show that even within a single genus, strategies diverge, evolution experimenting endlessly with the architecture of capture. As evening falls, the gold fades to amber and the web becomes nearly invisible. Dew condenses along its lines, each droplet refracting the last rays of light. The spider remains motionless at the center, her body poised in stillness that belies the constant tension around her. The air cools, humidity rises, and the silk once again softens, ready to perform its elastic dance when the first moths emerge from the undergrowth. To the uninitiated, her web might seem fragile, a transient artwork destined to vanish by morning dew or wind. Yet in truth, it is among the most advanced adaptive structures in nature, a living composite that responds to environment, resists mechanical stress, and harvests solar and biological energy alike. Its golden color, its tuning to air currents, its self-healing chemistry, all are products of natural selection's relentless refinement. The golden silk orb-weaver reminds us that engineering does not require tools, that precision can arise from instinct, and that the laws of physics are written not only in stone and metal but also in thread. The camera pans back and the web dissolves into light once more, a fleeting shimmer in the forest air, spun from sunlight, protein, and patience. In the quiet heart of a fallen tree, life continues long after the trunk stops drawing sap. Beneath its bark, the air smells of resin and decay, a mingling of death and renewal. If one were to press an ear, or better yet a contact microphone, against this timber, the silence would prove deceptive. Deep within, faint rhythmic sounds echo, soft gnawing, steady and deliberate. These are the jaws of longhorn beetle larvae, blind miners of the woodlands, tunneling through cellulose corridors that will one day return this tree to the soil from which it rose. Their work is both destructive and vital. Each larva carves its own gallery through the dense fibers, digesting with the help of symbiotic microbes that specialize in breaking down lignin and cellulose, compounds that most animals cannot touch. The result is an internal network of tunnels that gradually open the wood to fungi, bacteria, and moisture. In time, what was once a solid beam becomes a sponge for new life. The longhorn beetle's appetite, though seemingly parasitic, fuels the forest's nutrient cycle, transforming a corpse of cellulose into fertile humus. The larva's body, pale and smooth, fits the contours of its tunnel perfectly. With mandibles shaped like chisels, it scrapes and crushes fibers, its movements methodical and slow. It can take months, sometimes years, for a single individual to reach maturity, depending on species and climate. During this time, it navigates the labyrinth by touch and vibration. The head capsule, heavily sclerotized, acts as both battering ram and sensor, detecting minute changes in density that signal where bark ends or rot begins. This biological surveying ensures the larva remains within the optimal zone, neither too dry, which would harden the wood, nor too damp, which would collapse the tunnels. Eventually, metamorphosis begins. Within the hollowed chamber, the larva builds a pupal cell, sealing itself inside with a plug of frass and sawdust. Here, it transforms, tissues liquefying and reorganizing into the adult beetle. When the time comes, it chews an exit hole, often round and perfectly symmetrical, its edges sharp enough to suggest the work of a drill bit. The newly emerged adult steps into sunlight for the first time, its body lacquered in dark gloss, and most strikingly, crowned with a pair of antennae so long they seem to belong to another creature entirely. These antennae, sometimes exceeding the length of the beetle's own body several times over, are not ornaments but instruments. Each segment is equipped with thousands of sensory hairs that detect chemical traces in the air, pheromones, fungal volatiles, plant resins. To the beetle, the world is not seen but smelled in stereo. As it moves, the antennae sweep in graceful arcs, sampling microcurrents of air like living radar booms. Through them, the beetle perceives invisible landscapes of scent, the faint signature of a decaying oak, the pheromonal call of a mate, or the trace of a competitor hidden beneath bark. The longhorn beetle's olfactory precision rivals that of any insect on Earth. Some species can detect a dying tree from over a kilometer away, guided by volatile compounds released during decay. This ability ensures that adults lay eggs only in suitable timber, wood that is dead enough to be penetrable, but not yet overtaken by fungi that would outcompete the larvae for space. Their flight, slow and heavy, is adapted for short-range navigation through cluttered environments. Each wing beat seems cautious, deliberate, as though the beetle is reading the wind for clues. Yet for all its sensory sophistication, the longhorn beetle is vulnerable on open ground. Birds, lizards, and even predatory wasps find its flight sluggish and its body conspicuous. When startled, it can resort to an explosive escape mechanism known as kick launching. With a sudden contraction of the leg muscles, it propels itself backward or upward from a resting surface, a jolt of pure force that sends it tumbling into the air just fair enough to evade a grab. The movement is abrupt and surprisingly strong for an insect of its mass, a testament to the efficiency of its internal hydraulics. As dusk falls, the adult explores the boundaries of its wooden world. The forest floor is a patchwork of logs, stumps, and human structures, an ecological mosaic where natural and artificial timber intersect. On the edge of a wooden beam, a carpenter bee hovers, inspecting a borehole she herself excavated weeks earlier. The longhorn beetle, guided by scent and habit, seeks entry through the same aperture. Their encounter is brief but charged, a territorial dispute at the threshold of intersecting purposes. The bee, defensive and heavy-bodied, lunges first, producing a low, resonant buzz. The beetle holds its ground, raising its antennae like twin sabers. For a moment, evolution's two architects face each other, one who drills for brood, the other who mines for decay. Then, with a flick of its legs, the beetle retreats, disappearing into the shadows of nearby bark, while the bee resumes her work. The exchange ends not with violence, but with acknowledgement, each claiming mastery over a different stage of the wood's life cycle. The longhorn beetle's relationship with trees is ancient, dating back tens of millions of years to forests long vanished. Fossilized specimens show that their body plan has changed little, a testament to its evolutionary efficiency. The combination of strong mandibles, elongated antennae, and specialized larvae has allowed the group to occupy an ecological role few others can fill: the recyclers of dead wood. Their presence accelerates decomposition, preventing the forest from suffocating under its own detritus. Without them and other wood borers, carbon would linger trapped in lignin-rich tissue, slowing the turnover of nutrients essential for new growth. In certain regions, the beetle's work becomes audible even to human observers. On quiet nights, homeowners sometimes hear faint clicking or scraping within beams or walls. These are not ghosts, but larvae, the next generation continuing its ancient craft. The sound, amplified by resonance through dry wood, serves as a reminder that even our structures are temporary extensions of the forest. Given time, nature reclaims everything it provides. The same beetle that once tunneled through fallen logs may one day inhabit the remnants of a barn or fence post, transforming human material back into organic soil. Their contribution to biodiversity extends far beyond decomposition. The tunnels they leave behind become habitat for countless other species: solitary bees, parasitic wasps, spiders, and small beetles that depend on ready-made cavities for shelter or reproduction. In this sense, each longhorn beetle larva is an unintentional architect, sculpting micro-habitats that ripple through the ecosystem for years. Even the frass, the fine, powdery sawdust expelled from exit holes, becomes food for detritivores such as mites and springtails, continuing the chain of recycling at microscopic scales. The adults, though ephemeral, play their own part in pollination. Many species feed on nectar and pollen during their brief lives above ground. Their visits to flowers, while less deliberate than those of bees, help spread pollen across distances, linking plant communities in subtle but important ways. In tropical ecosystems, brightly colored longhorn beetles act as both pollinators and prey, their vivid markings serving dual purposes, warning predators of chemical defenses derived from plant toxins and signaling species identity to potential mates. As night deepens, the forest air cools and the scents of sap and fungus intensify. The longhorn beetle perches on a lichen-covered branch, antennae tracing invisible arcs through the air. The structure it left behind, a labyrinth of tunnels in a decaying log, continues to function long after its departure, hosting organisms yet unborn. What seems like destruction is, in truth, renewal. The beetle's miners, chewing unseen in the timber, are not dismantling the forest, but resetting it, converting the rigidity of death into the flexibility of life. The camera lingers on the surface of the wood, where faint vibrations can still be heard, the rhythm of jaws at work, carving the future from the past. Above, a soft thud marks the adult's takeoff, wings whirring into darkness. The long antennae sweep once more before folding against the night sky, and the sound fades into the chorus of crickets. The forest remains alive, not because everything grows, but because everything eventually returns. The surface of a still pond appears serene from a distance, a mirror of sky and shadow. Yet look closer, and you'll see a network of tremors, faint rings expanding outward in perfect symmetry like breath marks on glass. Each ripple carries meaning. They are not random, but language. The written script of the water strider, a creature that lives entirely between the forces of air and liquid. The strider is an insect that has learned to walk upon water without sinking, to hunt upon a boundary that would swallow anything less perfectly adapted. It is both acrobat and predator, using physics as a platform. Seen through a macro lens, the water strider's anatomy seems almost alien in its precision. Its legs are impossibly long and thin, 6 reed-like limbs poised with mathematical balance. The middle pair strokes the surface in oar-like motions. The hind pair acts as rudders. The front pair remains free, ready to seize prey. Each leg is covered in a dense forest of microscopic hairs, hydrophobic structures that trap air, creating a silvery sheath around every limb. This film repels water completely, forming a physical barrier that prevents sinking. The effect is so efficient that even when submerged by force, the strider bobs back up instantly, buoyed by the trapped layer of air like a living life raft. But their true secret lies not in anatomy alone, but in the physics they exploit. The water's surface tension forms an elastic skin, a meniscus, created by cohesive forces between water molecules. The strider's legs do not pierce it. Instead, they rest upon it, creating small dimples where pressure bends the surface without breaking it. These dimples act as footholds, allowing the insect to distribute its weight evenly across the water's elastic layer. To scale this at human size, imagine walking across a trampoline made entirely of liquid, every step requiring delicate calibration of pressure and balance. The physics of locomotion here defy intuition. To move, the water strider strokes backward with its middle legs, pushing against the meniscus and generating tiny vortices that roll beneath the surface. These spinning microcurrents propel the insect forward without splash or wake. The force applied is so precise that it converts the surface's elasticity into forward momentum. Each stride propels the insect body lengths in milliseconds, and then silence. No ripple betrays its path except for fading concentric circles. This mode of motion is one of nature's most efficient systems for surface locomotion, requiring almost no energy once mastered. Yet for the water strider, the surface is not merely a place to walk, it is a canvas of communication. Their world is written in ripples, each pulse carrying messages of intent, danger, or desire. Males court females through rhythmic tapping of their legs against the water, sending coded vibrations across the surface. The frequency and spacing of these pulses tell a female whether the signal comes from a suitor or a rival. A rapid series of tight ripples might indicate aggression. A slower, steadier pattern suggests courtship. To a human observer, these oscillations appear as delicate wavelets. To the strider, they are sentences, a full lexicon inscribed on liquid. This language of vibration has evolved from both necessity and constraint. Because sound travels poorly through air for a creature so small, and light can distort across water's shifting surface, the strider communicates through the one medium that connects every individual in its world, the meniscus itself. A single disturbance can be detected meters away, the energy transmitted faster than the insect can see. The ripples are not random static, but structured pulses, an ancient binary code of survival. When danger approaches, the tempo changes. A strider, sensing the heavy plunk of a fish's mouth breaking the surface, responds with a staccato of alarm ripples, alerting others nearby. The response is instantaneous. Within a fraction of a second, the surrounding insects scatter outward, skipping across the pond like black arrows. Each uses its acute vibration sensitivity to triangulate threats, avoiding predators that rise silently from below. But this same sensitivity makes the strider a formidable hunter. Its forelegs are lined with tiny mechanosensory hairs that detect the slightest tremor. The death throes of a trapped mosquito larva, or the chaotic flailing of an insect that has fallen into the water. The vibrations carry through the surface as distinct frequencies, the frantic, high-pitched tremors of struggle versus the slow, dying quivers of exhaustion. The strider's neural system interprets these patterns almost instantly. Within moments, it pivots and rushes toward the source. The strike is clinical. Upon reaching the target, the water strider pins it using its hooked forelegs, balancing delicately so as not to rupture the surface tension. The prey, often a mosquito or a gnat, is trapped in the film, unable to break free. The strider's needle-like mouthparts pierce the exoskeleton and inject digestive enzymes, liquefying tissues from within. It feeds not by chewing, but by drinking, drawing the dissolved contents through a fine proboscis. In less than a minute, the once buzzing insect is reduced to a translucent husk, drifting empty beneath the strider's shadow. Even feeding is an act of physics. The strider must maintain perfect weight distribution while handling prey. A single misstep or shift of balance could break the surface, plunging it beneath the meniscus and into the jaws of aquatic predators waiting below, fish, diving beetles, or backswimmers. Yet the strider's coordination is absolute. Its legs act as gyroscopic stabilizers, adjusting continuously to the smallest distortions. Every ripple it creates during the kill is dampened by calculated movement, ensuring minimal detection. The environment in which they thrive, ponds, marshes, and quiet backwaters, amplifies their mastery. They occupy a niche where few others can follow. Below them, aquatic predators patrol the depths. Above, dragonflies and birds cast shadows of death. The water strider's survival depends on its ability to exist between these worlds, light enough to avoid sinking, fast enough to flee from air or water attacks. It is a specialist of the in-between, thriving in the narrow margin where elements collide. Courtship, too, reveals a delicate interplay of aggression and restraint. Males often chase females across the surface, producing ripples that serve dual purposes, signaling interest while warding off competitors. Some species even exploit predator awareness as a form of coercion. A male may generate exaggerated ripple patterns, attracting the attention of underwater predators. The female, aware that lingering increases her risk, may accept mating more quickly to end the disturbance. It is a dark form of persuasion, one that uses the ecosystem's danger as leverage. Here, communication, survival, and manipulation merge into a single evolutionary strategy. As the scene shifts to the edge of the pond, a final demonstration of the water strider's mastery unfolds. The insect approaches the vertical curve of a reed, where water meets plant. The meniscus rises slightly against the stem, forming a steep incline of tension. To climb it, the strider performs a feat of surface mechanics few creatures could attempt. By pressing its middle legs downward and pulling upward with its forelegs, it deforms the surface just enough to generate lift, walking up the liquid slope as if scaling an invisible wall. The trick lies in redistributing pressure so that the meniscus supports the insect's entire body even at extreme angles. Step by step it ascends, legs dimpling the curved surface until it reaches the stem's base. There it transitions seamlessly from water to solid matter without breaking the surface film. Not a single droplet clings to its legs. This elegant exit marks the culmination of its design, the proof that the water strider is not merely adapted to water, but integrated with it. Every aspect of its biology, from hydrophobic hairs to vibration-based communication, operates in harmony with the physical laws of its environment. It does not fight the water's tension, it speaks its language. As twilight descends, the pond transforms again into a mirror, and the striders become silhouettes skating over liquid sky. The faint rings of their movements ripple outward, crossing, merging, and fading, messages written in transient geometry. For those who can read it, the surface of the pond is alive with conversation, the quiet pulse of life at the edge of two worlds. When the morning sun sweeps across the cobblestones of an old town square, the first movement on the ground is not human. It begins as a subtle flicker of red and black, a restless pattern crawling over the stone. Draw closer, and the illusion resolves into dozens, sometimes hundreds, of small insects, their shield-shaped bodies gleaming like polished lacquer. These are firebugs, Piracoris apterus, and they have turned the geometry of the human city into a landscape as precisely organized as any forest or meadow. Here, among cracks in pavement and the fallen seeds of linden trees, they have built a world of warmth, cooperation, and chemical conversation. Firebugs are a fixture of urban ecosystems across Europe and parts of Asia, a species so common that they often go unnoticed, mistaken for beetles or even ladybirds. Yet they are true bugs, belonging to the order Hemiptera, and their mouthparts tell the story. Instead of chewing, they pierce and suck, using needle-like rostra to tap into plant seeds, drawing out nutrients in liquid form. Their preferred food comes from the seeds of mallows and lindens, both abundant in parks and city streets. The ground beneath a mature linden can become a feeding arena, a miniature savanna of pods and shells where firebugs roam in tight clusters, feeding, mating, and basking. In early spring, when temperatures still hover near the edge of dormancy, the firebugs emerge from their winter refuges under bark, leaf litter, or masonry crevices. Cold-blooded by design, they rely entirely on external heat to power their metabolism. Unlike solitary insects that struggle to raise their body temperature individually, firebugs employ a remarkable strategy: aggregation. By clustering together on sunlit walls and stones, they form collective heat batteries. The mass of their bodies traps warmth, raising local temperature several degrees above ambient. Infrared imaging reveals these groups glowing faintly brighter than the surrounding rock, a living patch of thermal efficiency. Within these clusters, chemical reactions inside their cells accelerate, waking the dormant metabolism that drives digestion, molting, and reproduction. This communal thermoregulation carries real evolutionary advantages. Insects that warm faster can feed earlier, molt sooner, and reach reproductive maturity ahead of others. The warmth also accelerates the development of eggs and nymphs. Studies show that in aggregated groups, firebug larvae can complete their development nearly a week earlier than those kept alone under identical conditions. This efficiency has allowed Piracoris apterus to thrive in temperate climates where temperature fluctuations would otherwise slow their life cycle. They have effectively outsourced individual thermoregulation to the crowd, an insect version of urban heating. Their red and black coloration, striking under sunlight, is more than decoration. It serves as a aposematic warning, a visual declaration of chemical defense. Firebugs produce distasteful compounds in their hemolymph, derived from the breakdown of plant metabolites. These chemicals deter predators like birds and small mammals, which quickly learn that the bright insects taste foul. The pattern itself, with bold contrast and symmetry, acts as a cognitive shortcut in predator memory. Bright red means danger, or at least unpleasantness. Evolution has turned their social clustering into a visual amplifier, a congregation of warning signals impossible to ignore. The midday heat transforms the aggregation into a bustling colony. Beneath the human gaze, the insects move with purpose, their interactions precise and patterned. Some probe fallen seeds with their rostra, their heads tilted downward as they pierce the hard outer coat. The process is delicate. They inject digestive enzymes that liquefy the seed's starch and fats, then draw the contents back up through a capillary-like channel. Others engage in the peculiar ritual of tandem walking, a behavior seen during mating. The male, after copulation, remains attached to the female by his genitalia, facing the opposite direction. The pair moves together, a two-headed creature navigating the ground, as the male guards his mate from rivals until she lays fertilized eggs. This post-mating escort, sometimes lasting hours, may seem cumbersome, yet it ensures genetic success. The male prevents subsequent suitors from displacing his sperm, a common evolutionary tactic in species where females mate multiple times. The result is a slow, steady procession of coupled firebugs winding across the stones, their red bodies bright against grey concrete. To human eyes, they appear aimless. In truth, their movement is mapped by microclimates of heat and the scattered availability of food. City architecture shapes their distribution more than one might expect. Pavements and curbs create predictable gradients of temperature and exposure. Vertical walls absorb sunlight and release it slowly, forming heat reservoirs where firebugs gather in the morning and again in late afternoon. Cracks between paving stones serve as safe passageways, connecting feeding sites to resting zones. The entire microcosm functions like a planned neighborhood, each feature of urban design repurposed for insect survival. Even the linden trees lining streets play dual roles, canopy for shade and supplier of sustenance. In late summer, their seed pods litter the ground, creating a dense layer of resources that sustain entire firebug populations into autumn. Within this network, chemical communication binds individuals together. Firebugs rely on cuticular hydrocarbons, waxy surface compounds that carry species-specific scents. These molecules help them recognize kin, find mates, and maintain social cohesion during aggregations. When disturbed, they can release volatile alarm pheromones, triggering rapid dispersal. The same chemistry allows them to synchronize behaviors such as basking or migration between feeding and resting sites. Beneath their simple exterior lies a sophisticated system of chemical information exchange, the olfactory equivalent of citywide radio signals. Their relationship with heat goes beyond mere comfort. It is embedded in their physiology. Firebugs exhibit a unique adaptation in how they handle temperature extremes. During cold spells, they can lower metabolic activity and enter a reversible dormancy known as diapause. In this state, enzyme systems slow, conserving energy until warmth returns. However, in the fluctuating climates of urban landscapes, complete dormancy is rarely necessary. The warmth of stone facades and asphalt surfaces often provides microclimates that keep them active far longer than their forest-dwelling relatives. In this sense, the modern city acts as a climate stabilizer, a refuge of constant warmth amid seasonal chaos. The interplay between firebugs and urban heat exemplifies how evolution can pivot from forest ecosystems to man-made environments. Originally adapted to the warmth of tree trunks and rocky outcrops, the species has repurposed the concrete and brick of human settlements. Their success mirrors the city's own thermodynamics. Both capture sunlight, both redistribute heat, both depend on structural density to maintain stability. It is no coincidence that firebugs flourish near human habitation. Our construction inadvertently mimics the thermal conditions they evolved to exploit. Predators, though few, do exist. Spiders occasionally ambush nymphs, and some birds attempt to eat the adults despite their chemical defenses. Yet these pressures are minor compared to the hazards of desiccation or cold. Aggregation mitigates both, creating pockets of humidity beneath clustered bodies. This communal buffering effect keeps the insects alive even in harsh conditions, another layer of engineering in their collective design. As the afternoon wanes, the colony's energy shifts. Some individuals retreat into crevices. Others remain exposed, absorbing the last of the day's heat. The temperature within the cluster falls slowly, but the mass retains warmth longer than any single insect could. Thermal imaging once again shows the pattern, a fading glow pulsing with residual heat like embers in a fire pit. By nightfall, the square returns to stillness. To a passerby, the stones appear empty. Yet beneath a fallen leaf or within a crack in mortar, dozens of firebugs remain, drowsy but alive, sustained by the warmth of each other. They are not architects in the human sense, yet their behavior embodies principles of urban planning, zoning, resource distribution, and shared infrastructure. Every wall, curb, and pavement becomes a component of their living city, one that functions without intention, yet with the efficiency of design. The firebugs do not know they are engineers, but in their aggregation, in their use of heat and space, they have mirrored our own instinct to gather, to build, to share warmth against the cold. When dawn returns, they will re-emerge as they always do, spreading once more across the sunlit stones. The city's first inhabitants to rise are not people, but these red and black citizens of the cracks, the thermal planners of the insect world, writing their history not in architecture but in warmth. In the dim underbelly of Madagascar's tropical forests, where humidity drapes the air like a heavy curtain and decay perfumes every breath, a soft hiss cuts through the stillness. It is not the wind or the leak of gas, but the exhalation of an insect, a creature that breathes through its armor and speaks in air. From beneath the layered mulch of rotting leaves and fallen wood, the Madagascar hissing cockroach emerges, gleaming like dark bronze in the filtered light. It is both janitor and engineer, part of a silent workforce that converts death into life, waste into renewal. Unlike the winged urban cockroaches that haunt human nightmares, this species is wingless, slow-moving, and strangely dignified. Its body is shaped like an armored submarine, low, broad, and divided into segments that rise and fall with each breath. Across its surface runs a pattern of fine ridges, a microtexture that channels moisture and prevents the growth of mold. In the perpetual damp of the forest floor, such architecture is essential. The cockroach's exoskeleton is not merely protection, it is a living airframe designed to stay clean, shed debris, and regulate temperature. Each plate overlaps the next like flexible armor, allowing the insect to squeeze through gaps as narrow as a few millimeters without damage or loss of mobility. But what truly sets this species apart lies hidden beneath those plates. A respiratory system unlike that of almost any other animal. The Madagascar hissing cockroach does not breathe through its mouth or nose. Instead, it draws air through tiny openings along its sides called spiracles. These valves connect to a network of branching tubes known as tracheae, which deliver oxygen directly to tissues. The efficiency of this system allows the insect to survive in oxygen-poor environments, such as the compact layers of decomposing vegetation that form the forest floor. The air is thick with carbon dioxide, and yet the roach thrives, its spiracles opening and closing in rhythmic pulses, regulating airflow with astonishing precision. From these spiracles comes the hiss, a sound that has fascinated biologists for decades. When threatened, the roach forces air rapidly through the openings, producing a burst of noise that can reach the volume of a human whisper. It is one of the very few insects capable of such audible, controlled sound production using its respiratory system alone. The hiss is more than alarm, it is language. Males employ distinct variations for different contexts. Short, sharp bursts to signal aggression during combat, longer, sustained hisses in courtship displays, and low rhythmic patterns to establish dominance within colonies. Each sound carries subtle acoustic signatures, frequency shifts, amplitude changes that communicate intent across the leaf litter. In a confrontation, two males square off like miniature machines, antennae sweeping, feet gripping the substrate. They inflate their bodies, raising the ridges along their thorax and begin hissing in bursts. The sound is a mix of intimidation and assessment. The louder and more consistent the hiss, the more likely a rival will retreat. Rarely does the encounter escalate to physical combat. The acoustic duel often decides the hierarchy. The dominant male claims the best sheltering crevices, where females congregate. In these colonies, social order is maintained not by violence but by breath, a democracy of air. Beneath the canopy, their environment is a mosaic of decay. Fallen leaves pile into soft mounds alive with invisible chemistry. Microbes break down lignin and cellulose, releasing nutrients. Fungi thread through the soil like veins. The cockroaches move through it methodically, consuming the decomposing matter and breaking it down further. Their digestive tract is a miniature bioreactor lined with symbiotic bacteria and protozoa that continue the work of decomposition. The result of this endless grazing is rich, aerated soil, a foundation for plant life. Each mouthful taken by a cockroach contributes to the cycling of energy within the ecosystem. A single colony may process kilograms of organic waste each year. While invisible to the casual observer, their activity shapes the forest's fertility. In captivity, biologists have measured their fecal output as a surprisingly balanced compost, containing nitrogen, phosphorus, and trace elements ideal for plant growth. In this way, they are the forest's sanitation crew, operating continuously without rest or recognition. The compost floors they inhabit are not refuse heaps but ecological laboratories, where transformation is constant and nothing is truly wasted. The cockroach's movements through this medium create microtunnels that allow oxygen to penetrate deeper layers of leaf litter. This simple act of burrowing prevents anaerobic decay, a process that would otherwise generate toxic gases like methane and hydrogen sulfide. In effect, the insects maintain the forest's ventilation system. Their constant stirring ensures that the chemistry of decomposition remains balanced between oxidation and reduction. The interplay of insects, microbes, and fungi turns chaos into order, producing the sweet, earthy smell that defines healthy soil. To survive in such a dynamic environment, the Madagascar hissing cockroach must remain impeccably clean. Dirt-clogged spiracles can suffocate an insect in minutes, so grooming is essential. Using specialized spines on its legs, it scrapes and polishes its antennae, legs, and flanks with meticulous precision. This behavior is more than vanity, it's maintenance. By removing debris and mold spores, the insect ensures that its air intakes remain unobstructed, preserving respiratory efficiency. Under magnification, the process is mesmerizing. The leg spines comb through the fine hairs of the antennae, each stroke clearing dust that could compromise sensory accuracy. Their grooming also prevents the spread of fungal pathogens, a constant threat in tropical climates. Unlike vertebrates, insects lack adaptive immune systems. They rely on external barriers and symbiotic microbes for defense. The cockroach's exoskeleton is coated with antimicrobial lipids, creating a chemical shield that inhibits bacterial growth. This, combined with mechanical cleaning, keeps the colony remarkably disease-resistant despite its dense living conditions. What might appear to be chaos on a compost floor is in fact a highly regulated balance of hygiene, airflow, and social organization. In the microcosm of their world, air and waste are currency, traded, recycled, and reused with perfect efficiency. The very act of breathing becomes a form of communication, while feeding becomes environmental management. The hissing cockroach's contribution extends beyond its own survival. It supports entire communities of smaller organisms that feed on its waste or shelter in its discarded exuviae, the shed skins of molting individuals. Beetle larvae, metes, and springtails inhabit these miniature ecosystems, continuing the chain of nutrient recycling. Their role in decomposition has earned them a reputation as one of nature's most efficient recyclers. In scientific research, they are used to study gas exchange, microbial symbiosis, and the physics of airflow through porous materials. Engineers have even analyzed their spiracle mechanism for potential applications in micro-ventilation systems, technology inspired by an organism that lives in compost. The precision with which they regulate pressure and airflow on such a tiny scale rivals that of advanced mechanical systems. When night falls, the forest floor comes alive with subtle luminescence, reflections of moonlight off exoskeletal gloss, the movement of countless decomposers at work. The hissing cockroaches are among the most active. They navigate by scent and vibration, using long, flexible antennae to sense the terrain. Their hisses echo softly through the damp air, blending with the croak of frogs and the distant calls of nocturnal birds. The sound, once startling, becomes part of the rhythm, the breathing of the forest itself. Each hiss marks an exchange of gases that sustain more than just the insect producing it. The air expelled from the spiracles carries moisture and carbon dioxide into the soil matrix, feeding microbial respiration. Even their discarded frass contributes structure to the ground, improving aeration and water retention. What might seem to humans as refuse is, in their world, resource. There is no waste, only transformation. By dawn, the cockroaches retreat beneath the surface, hiding from the rising heat. The compost floor they leave behind is subtly changed, a little richer, a little darker, and more alive. Their hissing fades into silence, replaced by the buzz of diurnal insects taking their turn. Yet their influence remains in every breath of soil, in every seedling that rises from the mulch they have refined. In the grand network of life, the Madagascar hissing cockroach occupies a humble yet vital role. It manages air and waste with the efficiency of an engineer, turning decay into foundation. It breathes through armor, communicates in sound, and keeps the lungs of the forest open. The hiss that startles us is, in truth, the whisper of the ecosystem's machinery, the quiet exhalation of balance restored. On a summer morning, when the sunlight cuts through the meadow in angled beams, and every stem trembles with hidden life, a small green shape moves deliberately across a leaf. Its form is geometric, all triangles and edges, a mobile piece of living armor glinting with dew. This is a shieldbug, sometimes called a stink bug, a creature whose design reflects millions of years of refinement in both defense and communication. To the untrained eye, it seems simple, a tiny shield-shaped insect, slow and harmless. But beneath that calm exterior lies one of nature's most efficient systems of protection, a body that fuses armor, chemistry, and social signaling into a single evolutionary masterpiece. The defining feature of the shieldbug is its scutellum, the triangular plate that gives the insect its name. It rises from the thorax like a sculpted shield, overlapping the wings and abdomen in a perfect compromise between rigidity and flexibility. Its shape deflects probing beaks and snapping mandibles, directing force away from vital organs. Birds often test such insects with quick pecks, but the wedge-like design sends their attacks glancing off, leaving the bug intact. Even small spiders and mantises find their grip slipping from the slick cuticle. The insect's very geometry is a deterrent. Armor shaped not just for protection, but for misdirection. Yet defense for the shieldbug does not end with its exoskeleton. Beneath the plates, nestled between the third pair of legs, lie its most distinctive weapons, a pair of glands that produce volatile defensive compounds. When threatened, the bug contracts the muscles around these glands, forcing a pressurized jet of fluid outward through small pores. The result is a sudden burst of odor, acrid, oily, and unmistakable. It is a mixture of aldehydes and alkanes, organic molecules that evaporate rapidly and cling to the air. To predators, it smells and tastes like burning rubber mixed with rancid fruit, an instant deterrent that can linger for hours. For vertebrate predators like birds or lizards, this chemical strike triggers both a sensory and behavioral reaction. The compounds irritate mucous membranes and receptors, causing discomfort that the animal quickly learns to associate with the insect's coloration and shape. Over generations, this has reinforced the shieldbug's aposematic display, bright greens, reds, or metallic coppers that signal its distastefulness. Even humans handling them experience the sharp, bitter scent that seems to stain the fingers. It is not lethal, but it is unforgettable. The chemical system, however, serves more than one purpose. Within shieldbug colonies, the same volatile mixture doubles as a form of communication, a chemical alarm that warns nearby individuals of danger. When one bug is attacked, the release of its defensive fluid spreads a message on the wind, threat detected.
Within seconds, others respond. Some retreat to safer positions on stems or the undersides of leaves. Others freeze, blending seamlessly with the foliage.
The same molecules that repel predators thus knit the colony together in shared vigilance. In essence, their defense is communal. One individual's distress becomes the group's early warning system. Such cooperative awareness is unusual among insects that are not social in the strict sense. Shieldbugs do not form hives or hierarchies, but they often feed and rest in loose aggregations, especially during the nymphal stages. These clusters, warmed by the sun and united by chemical signaling, create micro-communities where alarm and safety are shared. The communication extends even to reproduction. Certain pheromonal compounds derived from the same gland system can attract mates, proving that what begins as a weapon may also serve as invitation. The camera shifts closer to the mouthparts, a slender, segmented beak folded beneath the head. Shieldbugs are sap feeders, their diet drawn from the nutrient-rich fluids inside seeds, fruits, and stems. The beak is both delicate and deadly, a precision instrument that can pierce plant tissue with minimal damage. Once inserted, it delivers saliva laced with enzymes that liquefy cell contents, allowing the bug to drink the solution through a narrow canal. This feeding method, called extraoral digestion, demands patience and control. The bug must balance pressure and angle to maintain flow without clogging or rupturing the tissue. Each puncture is a microsurgery performed without eyes or tools, guided only by touch and internal hydraulics. While many insects feed on sap, shieldbugs specialize in seeds, nature's most concentrated energy packets. By targeting developing seeds, they access stored lipids and proteins, nutrients dense enough to sustain long growth cycles. This feeding behavior also links them to the seasonal rhythms of their environment. When plants flower and set seed, shieldbugs flourish. When the pods harden and dry, they disperse, seeking new hosts. Their survival depends on reading these temporal cues, aligning their reproductive timing with the reproductive cycles of plants. As the seasons change, so does the insect's appearance. Shieldbugs exhibit remarkable color morphing between generations, a form of seasonal camouflage tuned to temperature and light. In spring, the green individuals blend perfectly with new foliage. As autumn approaches, pigments deepen into bronze, brown, or crimson, matching the tones of aging vegetation. This transformation is not merely aesthetic. Pigmentation changes are tied to thermoregulation and physiology. Darker cuticles absorb more heat, allowing cooler season bugs to maintain metabolic activity under waning sunlight. Lighter colors in summer reduce overheating. The insect's body thus functions as both armor and solar panel, adjusting its hue to balance protection and temperature control. The shieldbug's exoskeleton is a masterpiece of self-maintenance. Like all arthropods, it cannot repair itself internally, so it prevents damage through continuous external cleaning. The insect grooms by bending its legs over its body, using tiny comb-like structures on its tarsi to sweep debris from its wings, antennae, and scutellum. This process keeps the cuticle's microtexture free from dust and fungal spores, which could otherwise clog sensory hairs or trap moisture. The waxy coating that gives the bug its sheen also serves a defensive function, repelling water and reducing microbial adhesion. Under a microscope, the cuticle reveals a pattern of minute ridges that create hydrophobicity. Droplets bead and roll off effortlessly, taking contaminants with them. The insect, in effect, wears a self-cleaning raincoat. Predators, however, are persistent. Assassin bugs, spiders, and certain parasitic wasps have evolved strategies to overcome the shieldbug's defenses. Some wasps, for instance, have learned to sting the bug in its softer ventral membranes, injecting eggs directly into its body. The wasp larvae feed internally, avoiding exposure to the chemical glands. Spiders, meanwhile, attack from beneath, immobilizing the legs before the insect can spray. Such evolutionary arms races drive refinement on both sides. The shieldbug's armor thickens, its chemistry strengthens, and its behavior grows ever more cautious. Despite these dangers, shieldbugs thrive in a wide range of habitats, from forest edges to agricultural fields. Their adaptability stems from physiological versatility. They can regulate water loss through controlled spiracle closure, endure mild dehydration, and survive brief exposure to sub-zero temperatures by producing glycerol-like antifreeze compounds. Some species even overwinter as adults, hiding in bark crevices or leaf litter, waiting for the warmth of spring to restart their cycles. In urban landscapes, shieldbugs have become silent beneficiaries of human infrastructure. They rest on the sunlit surfaces of walls and fences, using heat retained by stone and metal to accelerate digestion and egg development. They also exploit ornamental plants as food sources, blurring the boundary between wild and domestic ecosystems. Their presence, often mistaken for nuisance, is actually a sign of ecological health, a reminder that even the smallest creatures maintain the balance between growth and decay. As evening descends, the shieldbug's colors shift under the changing light. Its green fades into shadow, its shell reflecting the last glints of gold from the setting sun. If disturbed, it hisses faintly, the sound of air forced through a tiny valve, and releases a final puff of scent before disappearing beneath a leaf. The odor drifts briefly, a ghostly warning to others nearby. Within minutes, the meadow falls still again. In its quiet way, the shieldbug embodies the principle that defense is never one-dimensional. Its protection is not brute force, but a symphony of materials and messages. Armor that deflects, chemicals that communicate, and behavior that coordinates survival across individuals. Its world is one of subtle engineering, where scent can mean safety, and a shield is both barrier and signal. By dawn, when the dew returns, a new generation of nymphs will begin their slow ascent across the stems, miniature versions of the adults, still soft, still vulnerable. Within weeks, their cuticles will harden, their colors will settle, and their glands will mature, ready to contribute their voices to the chemical chorus of the meadow. For now, though, the air is still, carrying only the faintest trace of their alarm, the lingering signature of a species that defends itself not with silence, but with scent. At the first blush of dawn, when the air is cool and the streets still carry the hush of night, a blur of motion hovers in the light that spills across a balcony garden. It darts, stops, hovers again, wings beating so fast they dissolve into an amber haze. A visitor that could easily be mistaken for a bird, yet it is no vertebrate. This is the hummingbird hawk-moth, Macroglossum stellatarum, one of nature's most accomplished aviators and one of its most sophisticated navigators. In the space between petals and air, it moves with the precision of a machine, feeding, mapping, and remembering. Its world is not one of chaos, but of carefully calculated routes, repeated with near mathematical consistency. The hovering flight that gives the hummingbird hawk-moth its name is a mechanical wonder. Unlike most moths, it does not settle when feeding. Instead, it suspends itself in front of each bloom, its body held perfectly stable as its wings execute a figure-8 pattern. This motion allows lift to be generated on both the upward and downward strokes, a principle shared only with hummingbirds and certain nectar-feeding bats. To sustain this form of flight, the moth's wings beat more than 70 times per second, and every beat is controlled with instantaneous feedback from sensory organs at the wing bases called halteres. These gyroscopic sensors detect rotation and vibration in fractions of a millisecond, feeding data directly into the flight muscles. The result is a level of aerial control so refined that the moth can hover in gusting wind, reverse mid-air, or sidestep a competitor without breaking its feeding rhythm. Its musculature operates at an efficiency bordering on the extraordinary. The thorax is packed with asynchronous flight muscles, fibers that contract multiple times per nerve impulse. This allows sustained high-frequency movement without the fatigue that would cripple most insects. The energy to power this system comes from rapid sugar metabolism. Nectar, with its near-pure sucrose composition, is converted to usable energy almost immediately after ingestion. Within seconds of feeding, the moth's flight muscles are already burning the new fuel. The process is so efficient that its metabolism rivals that of a hummingbird in terms of energy throughput per body weight. Every wing beat is a combustion of sweetness, a literal burning of sugar to stay aloft. But hovering is only half of the story. The true mastery of the hummingbird hawk-moth lies in navigation, in how it finds and revisits specific flowers across landscapes that shift daily. The moth belongs to a guild of insects known as trapliners, animals that establish stable routes between reliable nectar sources. Like a courier on a fixed loop, it visits the same flowers at nearly the same times each day, memorizing spatial relationships between landmarks. Experiments have shown that these moths can remember the position of individual flowers for days, adjusting their schedules to coincide with nectar replenishment rates. This behavioral precision, usually associated with birds or mammals, represents a high level of spatial memory uncommon in insects. When the camera follows the moth's morning flight path, the scale of its mental map becomes clear. It weaves from one balcony planter to another, crosses a narrow street, pauses at a window box, and then climbs toward a rooftop terrace bursting with petunias. Each stop is part of a learned circuit, a route optimized over time for maximum energy gain. The moth's brain, though smaller than a grain of rice, handles this computation with ease. Within its mushroom bodies, regions specialized for sensory integration and memory, the insect builds a three-dimensional model of its foraging environment. Using visual landmarks, it recalls not only the position of flowers, but their profitability, how much nectar each provided on the last visit. The hawk-moth's eyes are equally advanced. They are adapted for crepuscular light, those dim hours between night and day when flowers still hold nectar, but few competitors are active. Their compound eyes contain enlarged ommatidia that gather more light than those of typical diurnal insects, allowing color vision even under twilight conditions. They can perceive ultraviolet patterns invisible to the human eye, helping them identify nectar guides that lead directly to floral throats. Each eye is also equipped with specialized neurons capable of high-speed motion tracking, crucial for stabilizing the image of a flower despite rapid wing movement. This neural compensation allows the moth to see the world as stable while everything else vibrates around it. In slow motion, the feeding behavior reveals choreography as much as physiology. The moth's proboscis, a coiled tube as long as its body, unrolls with a flick, aligning perfectly with the flower's corolla. It hovers inches away, never landing, its tongue extended into the bloom, while its body remains motionless in space. The slightest change in wind triggers micro-corrections in wing angle and amplitude. It drinks for a few seconds, retracts the proboscis, and then darts backward in a blur, a reverse thrust achieved by inverting the phase of its wing beat. This immediate control over thrust and direction, achieved without pause or hesitation, is what allows it to visit hundreds of flowers within a single foraging session. Urban environments have become unexpected allies to this behavior. Balconies, rooftop gardens, and potted plants form a patchwork of nectar stations across cities. The hummingbird hawk-moth, once confined largely to rural meadows and mountain slopes, now thrives among concrete and glass. Its traplines thread through human spaces, window boxes, courtyard planters, roadside verbenas. In effect, the city becomes a fragmented meadow stitched together by memory and motion. The moth treats apartment blocks as cliffs, streetlights as navigational beacons, and urban flowers as islands in an aerial archipelago. Where other pollinators falter amid fragmentation, this species adapts, its flight range and cognitive endurance allowing it to bridge the gaps. Such adaptation hinges on its exceptional visual learning capacity. The moth can recognize not only flower color and shape, but also spatial orientation relative to background contrast. In laboratory tests, individuals trained to associate a particular color with nectar continue to prefer it even when presented among multiple alternatives. This capacity for associative learning, coupled with rapid recall, enables the moth to refine its routes dynamically. If one flower patch is depleted or disturbed, it modifies the loop, removing low-value stops and incorporating new ones. Over time, its daily route resembles a self-optimized network, an insect-scale algorithm for maximizing energy efficiency. Behind this precision lies an equally remarkable adaptation in energy management. Hovering flight demands immense metabolic output, and the moth must balance intake and expenditure with near-perfect efficiency. Thermal imaging reveals how it regulates temperature mid-air. By altering wing beat amplitude, it can generate additional heat when cold or reduce output during hot conditions. Its thorax temperature remains remarkably stable, hovering near 40 degrees Celsius even in cooler dawn air. This thermoregulation allows consistent muscle performance regardless of environmental variation. Its abdomen acts as a radiator, dissipating excess heat through convective airflow as it hovers, a miniature heat exchanger evolved through millennia of flight refinement. In evolutionary terms, the hummingbird hawk-moth's design represents convergence, nature arriving at similar solutions in very different lineages. Birds, bats, and this moth all developed hovering through distinct anatomical pathways but identical physical principles. Each manipulates lift, drag, and inertia in cyclical symmetry, trading metabolic cost for maneuverability. But unlike birds or bats, the hawk-moth's simplicity of form belies a complexity of control. It achieves the same aerodynamic mastery without bones, feathers, or lungs, powered only by muscle, membrane, and instinct sharpened by selection. Predators test this mastery constantly. Bats hunt by echolocation, and the hummingbird hawk-moth's buzzing flight falls well within their detection range. To evade them, the moth employs unpredictable trajectory shifts, abrupt zigs and zags at high velocity. These erratic patterns, combined with acoustic interference generated by wing beat harmonics, make tracking difficult. During daylight hours, birds such as flycatchers and shrikes attempt to snatch them mid-air, but few succeed. Their small size, speed, and constant acceleration make them elusive targets. In the rare case of capture, the moth's body still contributes to ecological balance, a transfer of energy from nectar circuit to predator metabolism, one node-feeding another in the web of life. When night finally deepens and most flowers close, the moth withdraws to rest on walls, under eaves, or in the shelter of ivy leaves. Its body temperature drops rapidly, metabolism slowing to conserve energy. The proboscis coils neatly beneath its head, and the wings fold along its sides in a tent-like posture. The city hums below, unaware that among its structures, one of the most advanced aerial navigators in the insect world is resting, its internal map already primed for dawn. By morning, the loop will begin again. Each flight a repetition and a refinement, an unbroken cycle of optimization. What to human eyes appears as random wandering is, in reality, algorithmic elegance, a creature running a living computation of distance, reward, and time. In the network of flowers scattered across the city, every balcony becomes a node, every bloom a data point in the moth's memory. Its roots are invisible, but their efficiency rivals that of engineered logistics systems, written not in code, but in instinct and experience. Hovering once more in the light, wings slicing figure eights into the air, the hummingbird hawk-moth embodies the seamless fusion of biology and physics, of behavior and environment. It is a courier of pollen and energy, a master of memory and motion, and a reminder that intelligence in nature often emerges not from thought, but from the perfect tuning of body to task.